So we've been looking at splitting field extensions, and I have recalled this theorem which characterizes splitting field extensions, now called normal extensions. The main observation was that if you have one of the splitting field extensions, so an extension that is obtained by adding all roots of a bunch of polynomials, you consider it inside a fixed algebraic closure. This is the inclusion map. If you take any embedding of sigma in f bar, fixing f pointwise, then sigma actually takes k to itself. So it actually determines an automorphism of k. Any such embedding is an automorphism. And these embeddings we saw already are rather interesting. So that focuses attention on this group, the automorphisms of k fixing f. And this would lead to the Galois group and the Galois extensions. And these are sort of the nicest kind of extensions where you have the most beautiful theorems. So that's where we are going. So here's the definition. K over f be an extension. You can make this definition completely in generality. We let aught k over f mean be the set of all automorphisms of k that fix f pointwise. Set of all field automorphisms of k that fix f pointwise. So this is clearly a group, and you can, and if k is, let's say, the splitting field of a polynomial, splitting field of some polynomial, where fx is some irreducible polynomial here, then we saw that the elements of this group are going to permute the roots of this polynomial. So in that sense, this group should be thought of as the symmetries of the roots of this polynomial in this case. Okay, so that's sort of why we are originally interested in this group, if you are interested in solving polynomial equations. So there was a discussion of this when we introduced splitting field. You can go back and watch that one. At any rate, you have this group, aught k over f, which will be sort of the central object that relates field theory to group theory. In particular, while we are at it, I'm also going to introduce something called this fixed field. So let H be a subgroup of, this means subgroup. Then K upper H denotes all the elements of K that are fixed by every element of H. So this is all K in K such that sigma K equals K for all sigma in H. Remember, each sigma is automorphism of K. So this certainly still contains F. So this is some sub-extension. So if you give me a subgroup of this group, I get some extension in between. And this would also play an important role. So if I would do an example before going on, our standard example of splitting field extension has been Q adjoin 2 to the 1/3 and cube root of unity. So this is our K, let's say. So this is splitting field of fx equals x cubed minus 2, right? And up here in kx, this polynomial factors as x minus alpha 1, x minus alpha 2, x minus alpha 3, where these are 2 to the 1/3, 2 to the 1/3 omega, 2 to the 1/3 omega square. That's alpha 1, alpha 2, alpha 3, the three roots of this equation. Okay, so I claim ought k over q, so this is our f, is S3. This maybe I won't prove completely right now, but I'll show you how you get certain automorphisms. So for example, you have this subextension q omega. This is a degree 2 extension because omega satisfies x squared plus x plus 1 equal to 0. So this is isomorphic to qx mod that. So this is degree 2. And over on top of that you have k. If you call this one m, then k is m adjoint 2 to the 1/3. Right, you already added omega, so you add 2 to the 1/3. We argued already previously that the degree of the big extension is 6, so this one is 3 up here. So degree 2 on top of, and then degree 3 on top. So the claim is, if you look at x cubed minus 2, it's still irreducible in mx. Because if it was not, then it would have a root. It's a cubic. So if it was not irreducible, it would have a root in m. But that would mean that when you add that root, you already get a degree 3 extension. But this is only degree 2. So it has to stay irreducible. So prove this claim. This is, I'll leave as exercise. I just said it orally. So this stays irreducible up here, which means that this extension is just mx mod x cubed minus 2. So you obtain it by just adding a root. So we know, if you now take q bar, the algebraic closure, I can include m in here, and I can get an embedding of k in q bar by sending one of these roots to any other root of this irreducible polynomial. So given for each of these alpha 1, alpha 2, and alpha 3, I can send 2 to the 1/3 to any of those and get an embedding of k in q bar. So there exists sigma from k to q bar such that sigma of 2 to the 1/3 is 2 to the 1/3 omega, let's say. And sigma restricted to m is just identity. So I'm extending this inclusion. Now what does this sigma do? First of all, because k is a splitting field, since k is a splitting field, this embedding is an automorphism. That's sort of the key point up here on the right. Sigma is an automorphism of k fixing m, but if it fixes m, it fixes q as well. So now you have constructed an automorphism of, so actually let me write ought k over m, which sits in ought k over q, because if it fixes m, it fixes q certainly. Anyway, any field automorphism is going to fix rational numbers, because it takes 1 to 1 and so on. So what does this guy do? So this sigma takes 2 to the 1/3 to 2 to the 1/3 omega, but it fixes m point-wise, so it takes omega to omega. So now you have an automorphism of k that does this thing. And then you can figure out what it does to the other roots. It takes this to sigma of the first thing times the sigma of the second thing, which would be 2 to the 1/3 omega times omega. So that's 2 to the 1/3 omega squared, because it takes omega to omega, you see. And then 2 to the 1/3 omega square, by the same token, would go to 2 to the 1/3 omega times omega square, because omega would go to omega, which is 2 to the 1/3. So you have these three roots, alpha 1, alpha 2, alpha 3. Sigma takes alpha 1 to alpha 2, alpha 2 to alpha 3, alpha 3 to alpha 1. So we have constructed such an automorphism. So this sigma would correspond to the permutation 1 to 3. And similarly, you can construct an automorphism that corresponds to 1, 2 by looking at some other extension. And that would actually show that this automorphism group is S3. And once you have done that, and it would also follow from some general theorem that we prove in a little bit. Once you have done that, you could look at the subgroup generated by this 1, 2, 3. And what does it fix? Well, I claim it fixes omega. Of course, it fixes omega by definition. So sigma omega is omega. So if you look at kh, that certainly contains q omega. But again, by general theory, later we'll see that this is actually equal. So in this case, if you take that subgroup of the automorphism group, then the fixed field k upper h is this extension, q omega. So that's what these things sort of look like. So I did not, I suppose, introduce the words, but let me state a lemma and then I would be able to. Let k over f be a finite extension. Then the following are equivalent. So we'll state this now and prove next time. K over f is normal and separable. So it's a splitting field extension and every element is separable, meaning the minimal polynomials have all distinct roots. So if you're in characteristic 0, you are only talking about splitting field extensions. This second condition is redundant. This automorphism group has the same size as the separable degree of the extension, which is the same when it's separable to the usual degree. So the group order is same as the extension. And see, each a in k that satisfies a polynomial in fx that splits into distinct linear factors in the bigger field. Okay. And when any of these three things happen, we say that the extension is a Galois extension, and in that case, this group is called the Galois group of the extension, this ought k over f. Say that k over f is a Galois extension if any or all of these equivalent conditions of the lemma holds, and write ought k over f equal to Galois k over f. It's called the Galois group of the extension. We'll study these extensions